Hi there, Mr. Sutton here, bringing you this Pre-Cal Honors 4-5 lesson on logarithmic equations. In this one, we will be solving logarithmic equations, and we will use this to figure out the energy released by an earthquake. We're going to start off with a real-life problem on one of the most famous logarithmic scales, the Richter scale. The Richter scale measures earthquake strength on a scale from 0 to 10, using the following formula. Log of E equals 4.5 plus 1.5 m. The E is the energy in joules produced by an earthquake, and m is its rating on the Richter scale. So we're going to apply this to a specific earthquake. The Chilean earthquake of 1960, the most powerful earthquake on record, had a Richter scale rating of 9.5. Here's some pictures of that. Complete devastation, more powerful than anything before or after experienced, or at least recorded. We want to know how much energy this thing released using this equation and the Richter scale rating of 9.5. Pause the video and see if you can get this thing started. Alright, so there isn't much to do on this so far other than plugging 9.5 in for m. If we do that and crunch the numbers on the right side here on a calculator, we see that log of E is equivalent to 18.65. So that's all nice as far as it goes, but how do we get E by itself? We can't really divide by log because log itself is not a number or value. It's just an empty function. With functions, you have to undo them. How do we undo the log function? What do we do now? Well, there's two ways to go about this. One way, option number one, which you've already done this kind of thing before, is to put this expression in exponent form. So pause the video, and using the fact that log is really log base 10 if you don't see another base, see if you can solve this with exponent form. Alright, so putting this thing in exponent form, we're going to keep the base of 10, and we're going to switch the input and the output. So we're going to do 10 to the output, 18.65, equals the input of E. And now we just have to figure this out on a calculator. And we see that 10 to the 18.65 is equivalent to 4.5 times 10 to the 18th power. And that's going to be in joules because this is earthquake energy. So that was one way to do it, using exponent form. But now if you're the kind of person who likes to solve equations by undoing things on both sides of the equation, there's another way to do this process. And this takes advantage of the fact that if you raise a number to a log with the same base, the two bases are going to cancel each other out and give you whatever was inside the log. So for this one, for example, if we were to raise this expression over here to raise 10 to this expression over here, like do 10 to the log base 10 of E, the log would go away. But you can't just do that to one side of an equation. We have to raise the base to both sides of the equation. So this is kind of weird if you've never done it before. We're not going to raise both sides to 10. We're going to raise 10 to both sides. We're going to turn both sides of this equation into exponents and put them on top of a 10, like so. So we've got 10 to the log of E equals 10 to the 18.65. Now we know that 10 and log base 10 cancel, so that's just E on the left side. On the right side, we have this number here again, 4.5 times 10 to the 18. So just two different ways of doing the same thing, and they're both useful in different situations. Now just to give you an idea, now that we've got this new technique established of the real-life importance of this number, this amount of joules, is actually 20 times the energy released by the strongest nuclear weapon. Another fact, that's 50,000 times the energy released by the bomb that hit Hiroshima in World War II. So a whole lot of energy being released by this thing. And you might wonder, well, how come the Earth still exists if that much energy was released? Well, all that energy got released underground, and the stuff that the surface got here was just a fraction of that. Thank goodness it was only a fraction, right? Imagine what the whole thing would have done. Let's take a look at this next example. Now, one thing that our last example had that this one doesn't is we only had a logarithm. We had a single logarithm on one side. So different situation here. If you've got these two different logs, we can't just turn this into exponent form or raise 5 to everything. So it works a little bit differently, although in this case we wouldn't be raising 5 because this is log base 10. What we can do, we know how to condense logarithms now. So we can combine logs that are on the same side using those log rules we learned in the last lesson. Here, since we are subtracting the logs, that means we are going to divide their arguments. So we can write this as one big log of 100x plus 4 all over 3x. And now pause the video and see if you can finish this off using what we did in the last example. Again, base 10, so we can write all this stuff inside the log equals 10 to the 2. Or you can think of this as raising 10 to both sides. Either way, 10 gets raised to the second power. And 10 to the second is 100. We're going to multiply both sides by 3x, so that's going to be 300x. Subtract 100 from both sides. Divide by 200, and that'll leave us with 4 over 200, which we can reduce to 1 over 50. Take a sec to try this one out. This is the same stuff, but with ln instead of log. Now ln, remember, that's log base e, so we're going to raise e to both sides. That'll be x minus 7 equals e to the pi. And they said we can leave our answers in terms of e if necessary, so it looks pretty necessary right now. We're just going to add 7 and call this one done. Every now and then we see some weirdness like this where we have a log inside another log. So the key on these is you do have to undo both of these logs at some point. In terms of order, we have to undo the outermost log first. Otherwise, we can't even look at the inner log. So take a sec to do that and see if you can finish up the problem. See how far you can get on this one. So if we're undoing this outer log, that means I've got to raise 3 to both sides. So this will be just the stuff inside the log. Log base square of x equals 3 to the 1. And now I just have to undo the other log. So I'm going to do 4 to the third now. And that leaves me with x equals 64. We'll do one more problem here. Pause the video and see how far you can get on this one. All right, so for this one, we have a whole bunch of logs. We notice that there's more than one log on the right side, so we're going to use our log rules to combine those into a single log. In this case, since we're adding the logs together, that means we can multiply the things inside. So the right side, we can write log base 6 of 3 times x. And now at this point, this is a new situation. We've got one log on each side. So there's a couple ways you can handle this. One way is you can think about canceling out both logs by raising 6 to both sides of the equation. And that would get you whatever was inside on both of these. Another way you can think about it is if you just have a single log on each side and nothing else, and it's the same log, you can just cancel the same log on both sides. So we can just write x squared minus 28 equals 3x. But really what's going on behind the scenes is you are raising 6 to both sides of the equation. Anyway, let's keep going here. If you didn't get this far, then pause the video and keep going. All right, so at this point we have a quadratic. We're going to get everything on one side and try to factor this thing. So we'll have x squared minus 3x minus 28 equals 0. And numbers that multiply to negative 28 and add up to negative 3, that would be 4 and negative 7. Zeroing these both out here, we've got x equals 7 and x equals negative 4. And we're done, right? Well, no, not quite. There is one more thing we need to do. Logs sometimes come out undefined. We've seen this. If we try plugging in a 0 or a negative number to a log, we can't actually find the log of negative numbers and zeros. And you might remember that this is because of the way the log graph looks, where you have an asymptote at 0 and nothing before 0, or just the simple fact that you can't take a positive number, positive base, and raise it to anything that's going to give you 0 or negative. Anyway, whenever you get answers using a log equation, you need to kind of mentally go back and plug these into the original to see if everything works out. If we plug in 7, that's going to give us a positive log, positive log, positive log, so 7's fine. But if you plug in negative 4, you're going to end up with a negative inside the log over here, log of a negative number over here. Over here, you also end up with a negative. So negative 4 actually gives us a negative inside a log, meaning the original is undefined at negative 4, and we have to cross that off as an extraneous root. That means that x equals 7 is our only true answer on this problem. So that's it for logs. Till next time, this is Mr. Sutton signing off.